let me wait 1 more minute. This clock is definitely not correct. So, today we continue with was a gas, and the topic of today's lecture is superfluidity. Okay, let me first list a few experimental facts, and then we proceed with discussion. Well, people studied helium, so-called helium-4. This is bosonic isotope of helium, contrasts to helium-3. And what they discovered actually is very interesting behavior. First of all, in a specific heat, as a function of temperature, there was a point, 2.18 Kelvin, where specific heat has very peculiar behavior, and it depends as a logarithm over t minus t naught on both sides of this point. So it's kind of indication, as we discussed, that there is a phase transition and something happens with the helium below this T naught. Then the second observation was that there is no boiling point below T naught, so the thermal conductivity is actually infinity. Then there were experiments done by Georgian scientist Lefter Andronikashvili, who put bunch of disks inside a container with liquid helium and start to make like torsion rotations of this bunch of the disks. And what he observed, that actually the inertia momentum of the liquid, which should follow the disks, is much less than it is expected. Therefore, there was a discussion that not all liquid helium is actually following the bunch of the disks. Then there was a study of flow or liquid helium through the capillaries, and capillaries are pipes with very small diameter, and then it was discovered that the liquid helium can flow through these capillaries without friction. This was very important observation, which in combination with Andronikashvili experiments, so this is capillaries, allowed to invent the word superfluidity. So the fluid goes through the pipes without producing any friction. And then even more intriguing phenomenon was observed. I will list two. For those who would like to read more, I recommend a fantastic book of Richard Feynman, which is called Statistical Mechanics. This is a beautiful book in all respects, and the last chapters are devoted to helium and superfluidity, because Feynman himself made a very important contribution to the theory of superfluidity. So two other effects are so-called fontaining effect. So there was a container with liquid helium, which was cold. So this is a cold helium. And the environment outside was hot, and still the helium from cold moved to hot area in order to produce kind of fontaining effect. This is again very counterintuitive, because typically we know that it's other way around. The hot substance make cold substance hotter. Here it's other way around. So there is a flow from cold to hot. And then, last but not least, there was another similar effect called thermomechanics. So this is number 5. So this is Fontaine. And this is thermomechanics. Which means there were two containers connected with a small breach, a capillary, and in one container the pressure was P and temperature was T, and the second container the pressure was P plus delta P and temperature was T plus delta T. And again, very counterintuitively, the flow was from cold to hot in order to make the hotter substance colder. Usually it's other way around. Moreover, there were observed so-called entropy waves. Of course, nothing is wrong with that. And in a few minutes, I will try to convince you that it doesn't break any general laws of the nature. So there is no contradiction with the third law of thermodynamics. And the phenomenological explanation of this phenomena was done in terms of two fluids. So the idea was that the helium consists of two sorts of fluids, two components. If I'm plotting the density, there is a one component which I will call rho S, which is a superfluid component, and another component is normal component. So below T node, there are two components. One is that which is characterized by huge coherency and can flow without producing any friction. And there is still another part which behaves like normal liquid. And the competition between these two components, actually, in the phenomenological theory, and Landau was one among persons who invented it, was sufficient to explain all this phenomena. And I'm not going to give you theory on each and every phenomenon. I will just discuss some general things related to the superfluid particles. So what Landau did, in order to explain experiments, he suggested that to have this superfluid component, the spectrum of excitations should first of all be characterized by sound-like low energy mode. So for small p, this is sound-like, namely C dot P. And then there is another feature of the spectrum, namely there is a minimum around some P node, and there is a gap delta node. So this was completely phenomenological way. So Landau just invented this spectrum of elementary excitations, and then constructed the two-fluid theory, well, contributed to construction of two-fluid theory, as I said, to explain the superfluidity. We will mostly concentrate on the sound-like branch, part of the branch of excitations. So this, as we agreed, we will call phonons. Another minimum, which in the literature is called rotons, would be outside our discussion, at least today. So maybe on Wednesday, when I'm going to show you some slides, I will comment on what this roton minimum, why do we need this roton minimum in the theory to explain certain phenomena and experiment. Okay, this is a collection of experimental data and hint for theoretical explanation. And let me first start with the explanation of the capillary effect of superfluidity through the capillaries. So we discuss something which is called in literature Landau criterion. So let's zoom in this capillary, which I said is pipe. And we assume that there is a liquid, and helium is a liquid, flowing through the pipe in that direction. And let's introduce two coordinate systems. One is attached to the flow, so we just, like a boat following the flow. This will be coordinate system number 1. And the second coordinate system we will associate with the pipe. So we will be stick to the walls. So what does friction mean? How this friction works in theory? So the fluid can emit some phonons into the walls, and this is the way the energy is reduced, and this is the way the velocity of flow goes down. So the criterion tells when this phonon can be emitted and what is the condition for creation and excitation in the walls. Okay, we characterize fluid as whole with momentum. So momentum P is H times Q. And let's write down the energy by transferring from the system 1 to system 2. So the energy of the flow in the system associated with the pipe is equal to E prime plus P dot V. So V is velocity of the flow plus kinetic energy mv square over 2, where epsilon prime is the energy in the system 1. So this is the energy of excitations, if you would like. And this is the total energy in the system 2. So in order to have a friction in the system, we should fulfill the condition that epsilon prime plus P dot V should be negative. But the momentum measured in the system 2 compared to the momentum measured in the system 1, again, this is the energy of the excitations with the momentum P. This is a momentum P. V is a velocity of flow. So P in the system 2 is just equal to minus P in the system 1, right? Because the system 1 coordinate system is just sitting on the flow. Therefore, this scalar product will be negative, and we should write that epsilon prime E prime minus P dot V is negative, and therefore V should be bigger than epsilon prime E prime divided by P. So the critical velocity, which is E prime divided by P, should be the criterion when the phonon can be emitted to the wall, if any. Okay, so this very simple 4-line calculation is known as Landau criterion, and let's now see in which system this Landau criterion can be satisfied and in which system this criterion cannot be satisfied. Okay? So let's start with ideal Bose gas. So ideal Bose gas, E prime is EP is P squared over 2m. This is the energy of our quasi-particles. Therefore, the critical velocity is, we will take limit P goes to 0, we divide P squared over 2m over P. So this is limit P goes to 0, P over 2m, and this is 0. So the ideal Bose gas, as you see, cannot be the superfluid because the critical velocity is equal to 0. So the ideal Bose gas flowing through the capillary will emit phonons in the wall anywhere. So it cannot be a superfluid. This is conclusion number 1. Let's say Bogoliubov spectrum. Let's take Bogoliubov spectrum. Which we have discussed last time. So I remind you that the Bogoliubov spectrum, namely the spectrum of excitations in weakly non-ideal Bose gas, is given by equation which we derived, C squared P squared plus P squared over 2m squared, where the sound velocity C, I remind you, was C squared, was equal to one over m u q divided by volume times m. And question?
Why am I taking the limit where p goes to 0?
Because we find the criterion. We want to find the critical velocity. As I said, we allow this flow to flow with any arbitrary velocity. And we are looking for the upper bound, so the critical value of velocity, after which the phonons can be emitted. So here, as you see, the phonons can be emitted for any arbitrarily small velocity. So we agreed to characterize the strength of the interaction with scattering length. So this is then was 1 over m 4 pi h square a over m times density. And I would like to write the gas parameter explicitly, so I will multiply by a square and divide by a square. So I have 4 pi h square over m a square times n a cube. So this formula was derived under condition that n a cube is much smaller than 1.
Sorry? Yes, I didn't understand the first criterion. The fact that the DC equals to 0 implies that the phonon can be emitted as.
As I said, we need to plug in, this is the criterion. We need to plug in the dispersion of our excitations divided by momentum, and for each given value of momentum, we find the velocity. In particular, we are interested in very long wave limit of our problem, namely, we are interested to find if for given p there is some upper value or there is no. And we see that this critical velocity, so to say, doesn't exist. Because for any arbitrary p, and in particular p goes to 0, the velocity necessary, which is sufficient to emit phonon in the walls of capillaries, is proportional to p. Therefore, if we take p equal to 0, the velocity is going to 0, which means there is no critical velocity. You will see the second example, and you will see that there is a critical velocity. Let me speak for 2 more minutes, and you will see the difference. So, what we see here, as I said, that the critical velocity, the sound velocity in the gas of Bogolyubov quasiparticles, let me plot Bogolyubov quasiparticles, epsilon phi, this is mc. So for large momentum, as we discussed, it behaves as p squared over 2m. For small momentum, it behaves as c dot p. And the sound velocity is equal to h over ma square root over 4 pi gas parameter na cube. So our theory was derived under condition that the gas parameter is much smaller, namely the typical range of the interaction is much smaller compared to the mean distance between particles. So this is the essence of the gas parameter. Let's now apply Landau criterion to this situation characterized by Bogolyubov spectrum, and the critical velocity, if exists, should be limit when p goes to 0, epsilon p divided by p. So for the long wave limit, epsilon p is cp divided by p. I take limit p goes to 0, and this is equal to c. So what you see that if your flow goes through the capillary with velocity smaller than the sound velocity, which characterize the excitations, there is no way to emit phonons in the walls. This is what the criterion says. So if flow goes through the capillary sufficiently slow, it goes without friction. This is the explanation why it is superfluid. So what we need for superfluidity is that the excitations in the liquid phonons characterized by certain sound velocity, and if the velocity of the flow is smaller than the velocity of sound, then it is superfluid. So this is that simple explanation. And you see, I didn't do any calculations. Basically, following Landau, what I did, I just transferred energy from one coordinate system to another one, and the system is Galilean invariant. I'm talking about non-relativistic situation and nothing more than that. And let me, last but not least, comment on phenomenological Landau spectrum. So what will then happen? You see that in principle you're right. I don't need to take a limit p goes to 0. I just identify the velocity at each and given momentum and see how it scales if the momentum becomes smaller and smaller. So what happens for Landau spectrum? Of course, if we are talking about that definition, namely the differential definition when the momentum goes to 0, I'm fine to say again that if the flow is smaller, the velocity of the flow is smaller compared to sound velocity, then the liquid is superfluid. However, in more general ground, I need to write a tangential, also taking into account contribution from large momentums, and this tangential actually reduced me the critical value a bit, which means that still I can satisfy this criterion even assuming tangential at sufficiently large. Okay. I don't want to say more about that. As I said, I recommend you good reading of Feynman book, and let's come to another little paragraph or little chapter, which I will call wave function of a superfluid. Wave function of Bose-gas. Once again, you see that Bose-Einstein condensation has nothing to do with superfluidity. The Bose-Einstein condensation in ideal gas exists even for ideal situation, namely when there is no interaction. However, the ideal Bose gas, which perfectly pass through the Bose-Einstein condensation transition, is not the superfluid. So for superfluidity, however, it's necessary to have two ingredients. First, there should be Bose-Einstein condensation, and second, there should be interactions in the system. Therefore, superfluidity can occur only in the interacting Bose system, which nevertheless also goes into BEC state. Okay, we said that BEC, Bose-Einstein condensation,